É porque tem gente esperando que fosse transmitido, mas gravar.
O meu problema é que porque acabou que eu não consegui fazer nenhum, foi meio corrido, não consegui fazer nenhum teste de transmissão até. Então a gente decidiu que era melhor botar para gravar e depois colocasse lá. E realmente pode ser que alguém fique lá no YouTube esperando, né? Mas eu não sei
Não, não tem
como.
problema.
Não, tá. Mas já está gravando e eu não sabia que dava para ser tão enrolado assim, organizar, mas agora eu entendo um pouco o João lá. Então, eu vou passar a palavra para o Fariana, que vai introduzir o nosso palestrante, Wilton, e aí depois ele pode já iniciar. Fariana.
Bom dia a todos e todas. Antes de tudo, eu queria agradecer ao João e ao Murilo por terem me dado essa oportunidade de apresentar o Wilton. É uma tarefa que eu vou fazer com enorme prazer, por vários motivos. O Wilton foi meu aluno desde novinho, de iniciação científica. Depois também eu e o Pinheiro, que está aqui na audiência, orientamos o Wilton no doutorado. E sempre colaboramos, e mesmo depois no pós-doc, ele orienta junto comigo um aluno de doutorado, que é o Yuri Muniz, e nós nos tornamos grandes amigos. Então, não podia ter uma alegria maior de estar aqui apresentando o Wilton. Bom, o Wilton, como já ficou claro, ele foi aluno do nosso instituto, fez bacharelado aqui, e ele foi brilhante, né? Ele foi brilhante em todos os sentidos, porque ele não só aproveitou demais os cursos, terminou com magna cum laude, mas a parte de pesquisa também. Uma das primeiras iniciações científicas dele, talvez a primeira, ele já ganhou um prêmio não só de melhor trabalho do Instituto de Física, como também de todo o CCMM. E depois, em outra iniciação científica dele, ele acabou escrevendo um trabalho que está citado no Griffiths, por exemplo, que é um dos livros mais usados de eletromagnetismo em graduação. Então, ele foi realmente um ponto fora da curva assim, na graduação. E no doutorado não foi diferente, né? Ele fez um doutorado muito bacana e acabou sendo premiado por esse doutorado. Ele ganhou o prêmio de melhor tese da CAPES, de Física e Astronomia, do ano de, acho que 2015, se eu não me engano. E foi um ano que mais de 100 teses concorreram. Ele ganhou também o prêmio de menção honrosa, do prêmio de José Leite Lopes de teses da Sociedade Brasileira de Física. Então, realmente, não só na graduação como no doutorado, ele foi um cara assim, brilhante, e também não parou por aí, né? Ele foi fazer pós-doc fora, fez 3 anos de pós-doc em Los Alamos, com dinheiro americano, que mostra, né, que a nossa instituição está boa, né? Está formando, mais uma vez, está mostrando que a gente forma bem as pessoas. E aí, quando ele estava a ponto de vir para o Brasil fazer um concurso, os caras lá de Los Alamos perceberam, né, que não podiam perder o Wilton, né? Então, simplesmente contrataram o Wilton. Novinho, ele foi contratado como pesquisador do grupo de matéria condensada e sistemas complexos da divisão teórica de Los Alamos. Isso em 2018. E logo depois ele já ganhou um prêmio lá também, que, traduzindo aqui, eu vou chamar de prêmio jovem pesquisador, que era para ele fazer pesquisa em dinâmica não linear da interação da luz com a matéria em isolantes topológicos bidimensionais. Bom, o Wilton tem muitos interesses, ele participa de muitos projetos, ele lidera alguns desses projetos já com verba grande e tal, e são, em geral, projetos em nanofotônica, com particular interesse em metamateriais, plasmônica e ótica quântica. Mas ele também desenvolve pesquisa em matéria condensada, com interesse particular em transporte eletrônico, espintrônica, em modelos, em sistemas bidimensionais. Tá? Ele também trabalha com simulação usando métodos de elementos finitos, enfim. E não preciso dizer que, mesmo novinho, ele tem dezenas de artigos em revistas importantes da área, como Physical Review Letters, Nature Communication, Nano Letters, coisas do gênero. Hoje o Wilton vai falar para a gente sobre metasuperfícies moduladas espacialmente e temporalmente, e como que pode usar esse tipo de coisa para, vamos dizer assim, moldar ou manipular propriedades espectrais e espaciais da radiação. Como vocês vão perceber, o Wilton também é um excelente expositor. Então, Wilton, por favor, com a palavra.
Obrigado, Farina, pela introdução bem legal. Pedi para você fazer com as suas próprias palavras e não seguir só o Lattes, e foi bem legal. Foi muito bom ter a sua amizade, a do Felipe. Estou muito feliz de estar aqui de volta no Instituto, mesmo que não presencialmente, podendo dar um abraço em vários dos meus colegas que ficaram e os novos que chegaram depois da minha saída. Mas virtualmente é um prazer ver novamente aqui várias pessoas que foram meus professores durante a graduação e durante a pós, e alguns colaboradores e novos estudantes com quem eu tenho me envolvido na pesquisa, sejam alunos do Felipe ou do Farina. Gostaria de agradecer ao Murilo e ao João, que foi quem, na verdade, me convidou para participar do colóquio. E eu já havia mencionado com o Murilo e com o João na época que eu preferia apresentar o seminário em inglês, o que eu não contei para o Farina, para ele conseguir dormir bem essa noite. E, obviamente, eu posso falar em português, só que eu não vou ter a habilidade do Farina de pensar na tradução correta de vários dos termos técnicos que são utilizados atualmente na língua portuguesa, porque muitos deles eu não sei qual é a tradução. Então, para evitar esse ato vergonhoso de mandar um Porto English no meio da apresentação, que alguns dos meus estudantes, a Patrícia e o Yuri, já falaram que de vez em quando eu falo em português e eu mando um you know no meio da frase, eu prefiro fazer a apresentação em inglês. E, além disso, como vai ficar disponível no canal do Instituto de Física no YouTube posteriormente, por questões burocráticas aqui de Los Alamos, será melhor se for gravado em inglês. Pode me evitar algumas dores de cabeça no futuro. So, if you don't mind, I will change to English now. You also have this amazing pleasure to hear me speaking in English with my strong Brazilian accent that probably many of you also have, but it's really cool. Again, I just would like to thank everyone for the invitation and the participants for being here to hear me talk about some of our recent works. And I think I have to share the screen again. I'm sorry, I totally forgot about that. So here we go. Okay, let me put this in presentation mode. Can you guys see my slides? Okay, something just happened. Okay, there we go. Do you see it?
Yeah.
Okay, thank you. So
it's not in presentation mode.
It's not?
You can see the side small slides.
Let me try again. Okay, let me see. And now.
No, it's okay. We can see, but then you lose the surprise. We know already what the next slide will be.
Oh no! Wait a second. We can
slideshow. I believe if you click on slideshow, it would appear something.
Yeah.
And play from start. Yeah, left most one.
Okay. I just did it.
No, we still see.
I think you have to share your entire screen.
Oh, and share the entire screen. Okay, let me try to do that because I was sharing just the application. So maybe that is the thing. Okay, entire screen. Allow. Okay, I see. Let's see. And now.
Yeah, no, it's okay.
We can set the presentation mode.
Okay, that's good. So now you know, Murilo, for the next time you organize that everyone has to share the entire screen. Okay, so as Sarina mentioned, I'm a staff scientist in the group of condensed matter and complex systems in the theoretical division of Los Alamos National Lab. And I'll be talking today about some of the works that we've been doing about how to control photons in what's called non-reciprocal space-time metasurface. Before we jump into action, I would like first to thank many of my collaborators, especially those ones that are here on the left column, which are also co-authors of the works that I'll be talking here about, but also those that I have been actively collaborating recently, and also the students and postdocs that I have been interacting most frequently. I would say some of them from the Institute of Physics and others from LANO. I used some color theory here just for you to know, like blue, it's theorists, and red are experimentalists. And I would like to mention to you guys that we currently have an open position, and we are seeking for one experimental postdoc to join our team to work on demonstrating some of the various aspects of space-time quantum metasurfaces that I'll be discussing in this talk for basically the next hour, essentially. So if you're interested or you know someone that could be a good fit, please ask them to either contact me or my colleagues, Diego Dalvit and Abu Azad. This position may be also a student position for 1 year to come for an internship at Los Alamos, but at this moment has to be an experimental person. And we may have other positions in the near future. We're expecting on the results of some grants to have applied, and that those may involve theory and other experimental positions. So if you're interested, just shoot me an email, and then we can start to have some discussion and see if this is beneficial to everyone. So because this presentation is actually going to be available online later on the YouTube channel of the Institute, I decided to somehow break a personal rule and make an outline of the presentation, which I typically don't do it. But this will allow people in the future to just skip the parts that they are not interested and then go to whatever they want to hear about. And so in the talk today, I plan to give a very brief introduction on metamaterials and what's called phase gradient metasurface, and then jump into two of our most recent works, which are essentially related about the idea of a non-reciprocity applied in photonics for classical metasurface or for manipulating quantum light that we have published in these two journals. And if you're interested, you can get the reference from there if to read in more details, or contact me later on to discuss more. And at the end, I'll give a very brief summary of what we have accomplished over, I would say, the last year with our research. So light-matter interactions has been a topic of intense research, essentially over the past 2 centuries. And we know that the laws of electrodynamics, either classical or in many cases quantum electrodynamics, will describe how an object responds to an incident electromagnetic radiation. And how this interaction happens actually depends on various properties associated to the object, such as the composition and the various materials that atomic species that are involved in the interaction, but also depends on the different arrangements of the atoms in the different lattices that can form different materials. And in general, also the interaction will be dependent on the dimensionality of the system that we are investigating, which can generate different kinds of light-matter interactions. But not only the object, also the properties of the electromagnetic field affect how the interaction takes place. For instance, the wavelength, polarization, and intensity of light will determine whether this is a strong, weak, or some kind of weird coupling between light and matter. In many cases, though, that we're going to investigate light-matter interactions, the wavelength of the incident light will be much larger than the typical interatomic separations in the object. And typically, we're not going to resolve the fine structure to describe how the electromagnetic field responds to the how the object responds to the incident electromagnetic field, but we will actually parameterize the response in terms of some mean field effective optical tensors like permittivity, permeability, nonlinear susceptibilities, and so on and so forth. It turns out that for the majority of the materials or for all the materials that we have available in the literature or in nature, all these optical parameters, they can assume some very specific range of values. As for instance, we know that typically the permittivity and permeability for all the materials that we know, they are typically, one of them, it's positive. And depending on which one is negative, we can go from metals to ferrites or just work with dielectrics. But we do not know any natural material that typically presents simultaneously negative epsilon and mu to characterize their optical response. So some time ago, I would say about 2 decades ago, people started to wonder how can we, or if we can design materials that would allow to achieve these unusual values of different optical parameters, and which kind of interactions could happen so that we could realize negative permittivity and negative permeability materials. And indeed, these materials, they can be fabricated, and they are typically man-made systems whose optical response is determined not only by the chemical composition of the different atomic species that we use, but also by the architecture of this structure that is typically repeated periodically and that we call the meta-atom. And these kind of micro resonators, they tend to have strong interactions with an incident electromagnetic field and allow to obtain some exotic optical effects. And originally, these metamaterials, they were proposed to actually achieve what I was mentioning before, that are negative epsilon and mu, which also corresponds to a negative index of refraction. And some new effects that arise, and people were discussing at the time, was that these materials with negative refractive index were called left-handed materials, and they had this very interesting property that as light propagated through it and crossed the interface between the metamaterial and natural material, the transmitted light ray would stay on the same side of the normal as the incident field, as demonstrated experimentally here, which is completely different from what is typically seen in the case of an interface between two naturally occurring materials, where the transmitted ray crosses the interface between the materials. And probably another very important application of metamaterials that came a few years later was the possibility of designing these materials in such a way that the refractive index would be position dependent, and then light could just be bent around a given region of space, making this area here, or this volume, completely hidden from the external world. So the metamaterial, as you can see here, would just therefore work as an invisibility cloak. And various other non-trivial effects have been proposed and experimentally demonstrated over the last 2 decades. But typically, interaction with metamaterials requires length propagation distances so that we can induce some kind of strong light-matter interactions. And this makes these metamaterials necessarily to be 3-dimensional, really bulky. And there are various challenges associated to bringing them down to smaller and smaller scales and integrating with existing technologies. So over the last few years, people in the metamaterials community have been really thinking on how can we control the flow of light, but using much smaller features, or not relying necessarily on 3D bulky materials. And inspiration to answer that question came from some very simple example that we see in every electromagnetism course. So we know, for instance, that if we send electromagnetic radiation and it crosses the interface between two media with different refractive indexes, because the phase of the field has to be continuous across this interface, we generate some reflected and refracted fields that will propagate in directions that are completely different from that of the incident beam, with the amplitudes of the field being completely determined by what we call the Fresnel reflection coefficients that are in general complex quantities. For the case of homogeneous interfaces, one can show that the direction of propagation of transmitted and reflected light, they are actually given by the standard reflection law and by the Snell law for the refracted light. So this already suggests us that using interfaces could be a way to actually manipulate and change the direction of propagation of light. So in 2011, the group of Professor Federico Capasso at Harvard started to consider the possibility of embedding nanoresonators at the interface between two materials, so to create a phase gradient that would modify locally the phases of the transmission and reflection coefficients. And they started to ask if that would potentially allow to control the direction of propagation of the reflected and transmitted beams. And this is essentially how the field of metasurfaces were born, and which are essentially two-dimensional versions of metamaterials where all the interaction of light with the nanostructures happens across an interface, with typically the thickness of the metaatoms being much smaller than the wavelength of incident light. And in that work by the group at Harvard, they actually showed that locally, if we use the Fermat's principle, we need to generalize the reflection and Snell laws, and now the transmitted and reflected angles for these two light beams, they need to be corrected to account for a gradient that we are applying along the interface, and therefore we're going to see that they can be directed and not follow the standard laws of reflection and refraction. So they have used these equations to design some very interesting metasurface and bring into place this new idea of a metamolecule that it's rather than repeating one single structure periodically, you construct a bigger feature that has many metaatoms, and that is the quantity that's actually being repeated periodically along the interface of the material, and they call that a metamolecule, which I find a really smart name to give it. And for instance, for this kind of metaatoms, it's possible to show that we create a phase gradient along the interface that changes linearly with position. So if you look along this direction, this phase is just going to be a constant times x. And in that case, these gradients here are just constants. So we can easily solve these equations to realize what are the directions of propagation for reflected and transmitted fields. And the experimental data actually shows that if we send light, for instance, at an incident angle of 30 degrees, we would expect it to be reflected at an angle of minus 30 degrees. But you see here from the experiments that depending on the wavelength, a wide range of different reflection angles can be achieved. And this is in some sense anomalous reflection or anomalous refraction. Some people even call it negative reflection or negative refraction. And these equations, although I should say their derivation is not 100% rigorous because these interfaces are actually inhomogeneous and we need to do full electromagnetic theory to derive the correct expressions for the scattered field, they work surprisingly well. And other examples that use more complex phases that have been demonstrated in the literature consider, for instance, the case where rather than arranging the metaatoms in a metamolecule and repeating it in the x and y directions, they decided to do it, putting it along some azimuthal direction so that they could demonstrate that this metasurface could generate, for instance, orbital angular momentum of light transmitted through the metasurface. And there are many other applications that you can find in the literature. I really recommend looking into this review paper that covers basically all the advances that were achieved in recent years. So, but many of these applications that have being demonstrated, they started to point out in which direction the field should grow in the future. And that's where we are trying to look here at Los Alamos, is what are we going to do with these metasurfaces if you want to move forward and bring these to real technologies that we can get off the shelf. So various groups have, some sense now, pushed the research directions to actually use metasurfaces for biomedical applications, or a topic that I like very much, which is actually to integrate metasurfaces with two-dimensional materials to realize different kinds of exotic electronic transport or photonic effects associated to light scattering from this combination of strong light-matter interactions at an interface with another two-dimensional material that is also an interface. And probably the two topics that we've been thinking more carefully here, which are essentially related to the integration of metasurfaces with computer interfaces, so that we could benefit from very powerful tools that have been developed in the areas of machine learning and artificial intelligence, for instance, for doing smart imaging and sensing. And more recently, also people have started to look at how to move these metasurfaces into the quantum realm, either to use them as standard optical elements that we have in the laboratory, replacing the ones that have like mirrors and lenses, or to use them to realize some other of different features using quantum light. And what we've been interested in these two topics, it's actually to consider metasurfaces that operate beyond the static regime. So they are not only manipulate light spatially, as I have mentioned before, but they also allow to control light in time, which we call, as I'm going to mention in the next few slides, spatial temporal control of a metasurface, because we're going to be interested in modulating light spatially and temporally, both continuously. And the interest on that, it's because once we add temporal control over to light, we are actually able to break some fundamental laws of electrodynamics that will give rise to, therefore, some very interesting effects. So because I'm going to talk about time control of optical interactions, there is no way to not discuss about what the meaning of reciprocity in photonics and what it means for light-matter interactions, which I plan to do in the next few slides. So reciprocity means going the same way backward as forward. And it's a word that we are used to see in our everyday life, especially when we're talking about relations between, let's say, different countries or different people. But it also has a formal definition from electromagnetism that we can understand by looking into two very simple experiments. Consider, for instance, that we have a light source that generates radiation with some frequency omega, momentum k, polarization, and any other property that we want to think, and that it sends light towards a detector. And in the middle, we have an object that we want to know if that object is reciprocal or it is not non-reciprocal. So in principle, our detector will measure the scattered light from the object, and that could potentially be measured in a different frequency, momentum, and polarization, so a different mode from the incident one. But once we make this detection, we can define a scattering coefficient that's just the ratio between the detected and transmitted fields. Now we do exactly the reverse experiment by changing the positions of source and detector, and again calculate the new scattering coefficient associated to detected and transmitted fields. So if these two coefficients from the forward and reverse experiments are identical, the system is therefore said to be reciprocal, and there is a clear relation between the forward and the reverse problems. Formally, we say that a system is reciprocal if the scattering matrix relating the input fields A and the output fields B in a multiport system is a symmetric tensor, so it is equal to its transpose. And obviously, computing these matrix elements can be very simple, as for instance, for the case of linear systems, where linear superposition principle can be just directly applied, but can also become really cumbersome if we're working with nonlinear systems and we need to consider inputs through different ports. So obviously a natural question that raises here is, can we establish a general relation that tells us when a system is going to be reciprocal or not? And that's precisely the content of the Lorentz reciprocity theorem in electromagnetism, that establishes that for any material that it's linear, has symmetric optical tensors, and the material is time independent, that the scattering will necessarily be reciprocal. So I should comment here some subtlety associated to my schematics. That is to notice that when I say that in the reverse experiment, we exchange the positions of source and detector, is just an issue of moving the source on the left to the right and the detector on the right to the left. Because notice that in the reverse experiment, the source that I'm using is not the same source as in the forward experiment. It's actually a source that emits radiation with the same properties of light that was detected in the forward experiment. And this, if you look in this picture, then we can have a general impression that the reverse experiment looks just like the time reversal symmetric version of the forward one. And that may lead us to wonder whether or not there is a relation between time reversal symmetry and the concept of reciprocity. And indeed, there is. We can actually show that if a system is time reversal symmetric, its evolution in the forward process, it's exactly the opposite of the evolution in the reversed process, and the system will necessarily be reciprocal. However, there are situations where we can have reciprocity but not have time reversal symmetry. And this is typically what happens, for instance, in lossy systems. Here, for example, if we look at the energy storage in a system and how it changes with time, we see that as time goes by, the energy storage will decay as a function of time because of losses. If we then do a time reversal symmetry operation and look into the evolution of the time reversed state, you see that energy will continue to decay as a function of time, because at the end of the day, the system has only losses. So we end up with a state that's different from the original one. And this means that we have broken time reversal symmetry. However, the system is purely reciprocal, because if you do the ratios between the power in the final and the initial states, which is here for the reverse problem, and the power in the final and initial states for the initial, for the forward process, we get exactly the same value. So it's very important, therefore, to have this in mind, that time reversal symmetry implies reciprocity, but reciprocity not necessarily means time reversal symmetry. So it turns out that most of photonic systems and problems that we investigate, they are reciprocal. And these could have some potential detrimental effects if we're looking for applications in the area of photonics. For instance, when we have a device that's trying to send information to some detector, but there is some defects and scattering happening in the environment that will generate parasitic reflection that will be sent back to the device and may interfere with its operation. So reciprocity is not always desirable. And in some cases, what we actually want is non-reciprocity, which literally means the absence of reciprocity, which has some kind of obvious applications, like, for instance, achieving what is called optical isolation, which we can do, for instance, by assuming that if we have a non-reciprocal device, that we put right after a non-reciprocal isolator that we put right after the device that is sending our signal, it will allow the information that we want to send to move only unidirectionally. And even if there is some parasitic reflection, it will filter it out, and no interference with the device due to back reflection will actually occur. So formally and mathematically speaking, the idea of non-reciprocity comes if we just have a scattering matrix that is not symmetric anymore. So if we find a pair of elements of ports ij where if I swap the positions of source and detector and they are not equal, the system is non-reciprocal. And this is a very clear definition, and I don't know how actually can be clearer, but still there are lots of confusion in the literature about what is non-reciprocity and what is asymmetric propagation. And some really important papers have actually made mistakes in their own publications in claiming that they achieved optical isolation when they were actually not doing so. So a typical example that you can do the experiment today when you get home night, probably you are at home now, so when it's night, it's, for instance, if you have seen these American movies, typically when we have a suspect that goes into these interrogation rooms, you're gonna notice that the suspect is typically in a very bright room, while there are cops that are typically observing the suspect in a dark room, and both of them are separated by what's called a one-way mirror. That's just a standard mirror that they gave a fancy name. But the suspect is sitting in the interrogation room cannot see the cops, while the cops can actually see the suspect. And we could try to say that this is a non-reciprocal situation because only one can see the other. However, for most of the cases, I would say there is nothing here that's time-dependent. All the materials are typically linear, and all the materials involved have symmetric tensors. So according to Lorentz theorem, this should be a perfectly reciprocal situation. And what actually is going on here is an asymmetric light propagation. And what, just a very simple explanation, is that the bright room will generate so much light that the suspect is only going to see light that is reflected from the room where he's sitting, but light transmitted through the mirror from the dark room will basically not be resolved by the eyes of the suspect. And exactly the opposite situation happens with the cop, who will basically see light transmitted from the bright room, but nothing being reflected from its own environment. And a more, I would say, and you can do this experiment in your home, I was mentioning, because if you go during night today in a room that it's that has a window and the external area to that window it's dark, you will try to turn on the light in that room, and you're going to see that you're going to have a very hard time trying to see through the window. But if you turn off the lights, you're going to be able to see the external world very well, which is an interesting situation you can realize in your own home. But this is only asymmetric propagation. And there are other applications associated to, for instance, transmission and reflection in photonic crystal waveguides, where a given mode can be highly transmissive when it goes from left to right, but there is no transmission when it goes right to left. And this is asymmetric propagation, but it's a reciprocal system, because as I mentioned before, when we do the reverse problem, the source that we use needs to have the same properties of the light that was detected in the forward experiment. And if we do that, then we also have a transmission from right to left. And this is a very nice comment that you can actually access in science about some works that have had a misconception about non-reciprocity. So a natural question that we could have here is, how do we achieve them non-reciprocity? And the first thing is that Lorentz theorem does not tell us how to do non-reciprocity, but it does point out some directions. If we violate some of the conditions for its validity, we can start to realize non-reciprocity. So we could, in principle, use nonlinear materials, magneto-optical materials, or then use time-dependent materials. And all of them, they have advantages and disadvantages. And I could spend substantial time here talking bad things about these guys and good things about these ones, because the one I am interested. But I should say that depending on the kind of application that someone has in mind, they could have different utilities. So the one that I'll be concentrating is about breaking Lorentz reciprocity theorem through using time-dependent materials, where we have, for instance, the refractive index being modulated as a function of time. And we also, because we're interested in metasurface, we're going to be considering the possibility of also having some kind of spatial modulation with what we're going to be calling from now on an in-plane kick. You're going to see in a second why that is the case, where we can realize different kinds of non-reciprocity, as I will be discussing. So how do we realize this non-reciprocal devices, we typically need to develop metasurfaces or materials where we embed them with some kind of active element that we're going to modulate as a function of time. And here at Lana, what we did was to develop a metasurface that is based on this kind of split ring resonators, and we have embedded them with these active elements that are called varactors diodes, which are just electronic components that have a nonlinear relation between capacitance and voltage applied. And if we then change these voltages as a function of time and put a relative phase between the different channels of the metasurface, we are actually going to be generating a spatial-temporal modulation of the metasurface that should allow us to produce different scattering patterns of an incident electromagnetic radiation. Obviously, I am a theorist, and although I do some finite element method simulations, modeling the process of scattering through this metasurface, considering the microstructure of these metaatoms, can be very complicated. And we did actually something much simpler. That was actually to consider that our spatial-temporal modulated metasurface is just a multi-layer system, as we see here, where the entire layer of time-modulated metaatoms we're just describing as a two-dimensional conductivity, similarly to what we do with graphene when we are considering interactions with two-dimensional materials. But my conductivity now, it's also, it has some static component that comes from the static metaatoms, but we are also considering that we are changing these voltages in time, and that will produce a modulation of the conductivity with some amplitude, some periodicity in time, and we can imprint some spatial variation by controlling the delay between the different channels of the metasurface. With all the parameters here, we can extract from the experiment. And our task is essentially to compute what is the scattered field that we obtain when some incident radiation interacts with the metasurface. So it is, I would say, a complicated problem. But the basic idea is that if we have light coming with a given momentum and energy and coming to the metasurface, because we are modulating it spatially and temporally, we're going to have light scattered in many different directions, so many different plane wave components, and we need to sum over all of them. And because of the temporal modulation, we can also have frequency conversion that will generate light in different colors. And again, we need to sum over all those harmonics. And formally, the expression for this summation is what you see here. And in the case where we have a sinusoidal modulation and the phase gradient that we apply on the metasurface changes smoothly, we can actually draw some interesting relations between the scattered field and the input field. For instance, we can show that the frequency and the momentum of the harmonics and diffraction orders generated by the scattering, they are related to the input and frequency and momentum through the relations that I'm right here. And the most important feature that I want to draw your attention to is the fact that the index for the harmonic order and diffraction order for frequency and momentum is exactly the same in both cases because of the kind of modulation we're using. That means if we have an upper conversion in frequency, we're going to have an upper conversion in momentum. Down conversion in frequency, down conversion in momentum. Keep that in mind because this is going to be extremely important for our discussion on non-reciprocity. And in this expression for the total scattered field, there is here this quantity that are essentially generalized Fresnel reflection coefficients that we need to compute by enforcing boundary conditions. And we can show that those satisfy some coupled equations that involve different orders of harmonics appearing. And the only thing that I would like you to keep in mind is that these equations, they are essentially summarized in this diagram here, showing that the fundamental reflected mode will interact only with the very first two orders of harmonics, which then can interact with the plus minus 2, which then with plus minus 3. In general, however, we're going to be working with situations where this modulation amplitude of the spatial temporal modulation is very weak, and we can consider just coupling between the lowest harmonics. The cases that we have considered in details here in Leno is the most simple case where we have a phase that changes linearly with position and where these equations can be solved analytically because the reflection coefficients become position independent, and then the theory that we developed reduces to a standard Bloch-Fouquet expansion. And just to show you that these are indeed the guys that dominate the scattering, here is some of our experimental data for the reflection into the fundamental harmonic, which is in red, and reflection into the ±1 order harmonics of the system. And you notice the 10 to -2 here, already showing that reflection into the first two harmonics is much weaker than reflection into the fundamental mode. And we actually don't see the second harmonic being generated in the metasurfaces that we have investigated here. And we decided for future information, just to mention, to operate around this frequency because it's where we more or less maximize reflection into the first harmonics while keeping the fundamental harmonic relatively low. So what can we achieve in terms of non-reciprocity using these metasurfaces with linear phase gradients? So the first thing that we did was, for instance, consider that we have input light with some given frequency, and it impinges on the metasurface that is on the bottom, and then we calculate what is the scattered field in the first harmonic. And as I mentioned before, the input field can suffer many up or down conversions. If we look into the up conversion in frequency, also achieve an up conversion in momentum, and then reflected light will propagate in a direction that it's not normal, which is essentially anomalous reflection that I was mentioning before, but for the fundamental harmonic. To check reciprocity, we need to do the reverse experiment, which is to take this output field and send it back to the metasurface. So notice that to do that, I keep the same frequency that I had as an output, but reversing the field, I need to reverse the direction of the momentum of the electromagnetic wave. And now we look into this and I say, okay, I want to get back to my original field to check if I can get the system's reciprocal or not. So to go back from this frequency to the original one, I need to do a down conversion in frequency. But as I mentioned before, a down conversion in frequency also means a down conversion in momentum. And what happens at the end of the day is that although I can go back to the original frequency, I end up with the wrong momentum and light just propagates not normally to the metasurface, and we do not recover the original input state. When we did this work, we actually realized something that surprisingly no one did this before, that is to notice that the out-of-plane component of the momentum of the electromagnetic wave scattered in the reverse problem was given by this expression that you see here, and which is typically a real quantity if beta is below some critical value. But if beta goes beyond that critical value, this kz component becomes purely imaginary, in which case we expect to see no light being scattered off the metasurface, but only in-plane propagation associated to the excitation of a surface wave. So we decided to check if that was true, and then we did again our experiment, but choosing now a value for the in-plane kick much larger than the critical value. Again, the input gets light steered in some other direction, which is obviously bigger than that one because I'm giving more momentum to my output wave. But when we do the reverse problem, what we have noticed is that we can only excite light propagating in the plane of the metasurface. So we checked that our theoretical predictions experimentally, and you can see here the metasurface that we have fabricated. The meta atom is exactly the one that I showed in a few slides back with that split ring resonator, and you can see here the various control lines that we use to imprint the modulation of the varactor diodes. And then we did our measurements in an anechoic chamber, where you can see here where the metasurface is sitting, and then we have horn antennas, their source and detectors that are VNA controlled, and we mount them on a gimbal that we can rotate so that we can scan into different directions and to measure the scattered field. And we modulate the metasurfaces with a frequency of 50 kilohertz, and then we have a detection resolution of 0.1 kilohertz, which is more than enough to detect the generation of harmonics in our system. So the first thing that we checked was just putting normally incident light and changing the in-plane kick of the modulation of the metasurface to show that we can scatter the first harmonic into any direction that we want, essentially. But then we decided to check for reciprocity or non-reciprocity in our problem. So we did, for some value of beta, we did the Ford experiment and send the light impinging normally, check that it was scattered in the direction that we predicted theoretically, and then we did the reverse experiment. That was just to send the light back from the direction of the scattering field in the forward experiment. And first thing that we did, okay, let's see what field goes into the same direction as the original incident field, which means I need to take this momentum and bring it to zero. So I need to do a knot conversion in momentum, but that will result in a knot conversion in frequency. And although I can get some field that goes in the same direction as the input field, it has the wrong frequency. And this is what we call a frequency non-reciprocity. If we decide to look, however, at the field that goes into the same frequency as the original input field, we have to do a down conversion. And as I mentioned before, we do a down conversion in momentum. So I recover this original frequency, but I have the field going in the wrong direction. And again, there is a very good agreement between the theory and experiment. And finally, the case of extreme non-reciprocity, where we use a larger in-plane kick momentum. And this is what actually we see in the experiment, that there is a strong suppression of the far field scattered radiation, which is an indication that we are probably exciting surface waves in our system, which is again consistent with experiments. Okay, I think, how much time do I have? Am I too late or?
10 minutes, do you think is that fine or?
Well, can I have 15 more or less?
Yeah, 15, 20. Yeah, I mean, there is no reason to, yeah, that's fine. 15,
okay,
20 minutes.
Because, okay, I'll try to go faster in these next two slides, just to jump to the quantum part. So in addition to doing this theory and experiments for a linear phase gradient in our metasurface, we also consider a situation that no one did before, that was the possibility of demonstrating non-reciprocity for what is called a focusing or a parabolic flat antenna. So it's like the dish antennas that you have, we use it to have in our houses in the past, but it's perfectly flat. And because we have some spatial temporal modulation, what we try to do is to imprint in the metasurface a phase profile that will allow some given harmonic to be focused, but all the other harmonics will not be focused. We did theory to that to show that we can actually focus radiation for the fundamental harmonic, and we actually have verified experimentally that indeed is the case with, I would say, a reasonable agreement between the theory and experiment predictions. And if we want to check for non-reciprocity, then we need to take this output field, as I mentioned before, and send it back into the metasurface and verify whether or not the output from the reverse experiment is a plane wave propagating normally to the metasurface. It turns out that this is a very complicated problem where essentially the output field will be summing various contributions from different plots that look just like this one. Here I'm just plotting the amplitude of the field as a function of a position for the case where I take one given component of the incident field that impinges normally on the surface, but I look at the output component that goes into the direction that strikes the gradient of the phase. And we see that there are regions where we have only evanescent waves and regions where we have propagative waves, but nothing of this looks like just a plane wave propagating normally to the metasurface. So we do expect to observe non-reciprocity with this focusing phase. It turns out that the experiment is much more complicated for two reasons. One of them is that theoretically, I can just take my field from previous slide and invert all the momentum to make the reverse experiment. Experimentally, I cannot do that. So what we call a reverse experiment is that to use a monopole source to send the light into the metasurface, and then we try to check what happens in the far field. The second thing is that the metasurface has a finite size, which complicates a little bit the things. But we did a theory for that case, and we actually have predicted that for this situation, the reverse experiment should give some directions where we observe maximum emission of radiation in the far field. And we achieved a very good agreement, again, with the experimental results. And the most important feature you should keep in mind from this part here is actually that this field distribution does not look at all like a plane wave propagating off the metasurface, which is that as far as we know, the first demonstration of non-reciprocity for a flat antenna that focuses electromagnetic radiation for a given harmonic of light. So I will. This is our work on non-reciprocity in classical metasurface, and I will now change to our more recent works about quantum metasurfaces that are modulated in space and time. And our interest to this topic came when we came across some papers that were present in the literature, more specifically these two ones that I'm showing here, where they have worked with static metasurfaces that are made of these highly anisotropic metaatoms that are designed in such a way that they work as a half-wave plate device in such a way that left circularly polarized light will be converted to right circularly polarized light upon transmission, and vice versa. And if you combine that, and if you take these metaatoms now and you position them in a metasurface, putting a small twist between neighboring metaatoms, you can also generate a geometric static phase. And what is very interesting in this situation is that if the incident light is right circularly polarized, we get a linear phase gradient with a positive sign. But if we have left circularly polarized light, we have a phase gradient with a negative sign, meaning that right and left circularly polarized states, once they transmit through the metasurface, they will be kicked into opposite directions with different momentum. And this kind of spin-orbit coupling for photons has some very interesting applications, as for instance, if we send a linearly polarized photon into the metasurface, as it transmits through, we expect that we're going to generate a state where we have entanglement between polarization and linear momentum. And that's essentially what these two works have done in the literature, to using these linear phase gradients, or when you put the metaatoms in a circular, azimuthally distributed in the metasurface, to also entangle spin and orbital angular momentum of light. And we looked into this and we decided to say, okay, what happens if we also put a spatial temporal modulation on top of these geometric phases that induce spin-orbit coupling? So before doing that, I just should mention that there are a few more works on doing quantum with metasurfaces. They are all very recent and in very important publications, and they are really nice to read. I particularly like the middle one, if you want a suggestion for something to read here. Okay, so our idea then, as I just mentioned, was take this geometric phase static metasurface with spin-orbit coupling and put into them some kind of time and space modulation. And from now on, I'm going to be calling the phases that comes from rotating the metaatoms a geometric phase, because that we achieve just by geometrically designing the metasurface. And I'll be calling the phase that we imprint with the time modulation a synthetic phase that we can reconfigure on demand in our metasurface. And by combining them, we decided to call this a space-time quantum metasurface, which is this idea that we can develop a compact dynamic photonic platform where we can manipulate entanglement and hyperentanglement between different degrees of freedom, with potential applications associated to sensing, imaging, and also because we're going to be exciting harmonics and many diffraction orders, we actually can explore a larger region of the Hilbert space in what people were calling qubits, which are just qubits that are not just 0 and 1, but you can have 0, 1, 2, 3, 4 different states. So we looked into different kinds of applications. The first one was essentially what happens when we send a single photon through these metasurfaces where we have the metaatoms that are rotated among them, so we have a geometric phase, but we also have some kind of spatial temporal modulation and want to know what is the output state of the system. because we know what happens with classical light, we can guess what is going to happen with the output state from our metasurface. And we know that's just going to be a superposition of many frequency harmonics, many momentum diffraction, many spatial diffraction orders that depend on the spatial-temporal modulation. But there is also the direction of propagation depends also on the geometric phase, whose sign here and here depends on the polarization of the output photon in our metasurface. So for concreteness, what we have considered in our cases were this kind of cross-like structure that we have chosen the parameters in such a way that you can see here we can achieve very high transmission and cross-polarization at telecon wavelengths. And we have considered a situation we have also a null dielectric metatom so that we can minimize potential losses and the coherence from happening in the system. Obviously, because we are taking into account that this guy is all dielectric, we can start to wonder how can we modulate these metatoms spatial-temporally, since I cannot just go and apply an electrical bias to the metatoms, they will just not respond to that. And the idea that we came up with was to use these optical gratings that the way to generate them is essentially to use two pump beams that will interfere at the surface of at the metasurface and create an in-plane wave that has frequency given by the difference between the two frequencies of the pump beams and in-plane momentum that is given by the difference of the in-plane momentum of the two pump beams. And this is an experimental image of what we have done here at Lano of the optical grating. If these materials now have some kind of strong nonlinear Kerr effect, we can show that this optical grating will actually effectively modulate the permittivity of the metatoms as a function of space and time with a linear phase gradient. Again, as a theorist, modeling the interaction between this photon and these complicated structures can be really problematic. So we decided to simplify the problem. And we did that by realizing that in this wavelength range that we are working here, there are essentially 4 dipolar modes that dominate the response of the metasurface, 2 electric dipoles and 2 magnetic dipoles. And we decided to say then that the interaction between the photon and the metasurface can be just described by a multipolar Hamiltonian with the way that we are writing here. And because we are able to compute these dipole moments numerically, we did a further simplification that it's actually to express these dipole moments in terms of the polarizabilities. And we can compute those fully numerically. And also something that was very important to do at the time was to determine what is the relation between a variation in the permittivity of the metatom and what is the variation that we achieve in the polarizability, which can also be computed. So if you take this formula and then you just plug here, you're going to end up with this kind of one photon Hamiltonian that has many things, but there is some nice way to look into it. So you see here the annihilation and creation operators, and you see that they are combined with different polarizations, meaning that what this Hamiltonian does at the end of the day is to, let's say, for instance, annihilate a photon with right polarization in the mode gamma prime and creates a new photon with the opposite polarization in a new mode by adding also a geometric phase that can be negative or positive depending on the polarization of the input photon. And there are 2 contributions coming from the polarizability. One is the static polarizability, which together with this exponential here will mean that the output photon will have the same frequency as the input one. But there is a contribution coming from the spatial-temporal modulation, where we see that this cosine modulation will result in an output photon being Doppler shifted with respect to the input one, and we'll also add a synthetic phase to the output state. So by looking to this Hamiltonian, then we essentially solve Schrodinger's equation by by having this as our ansatz, where we need essentially to compute these coefficients, and we can show that there are 2 coupled differential equations that involve different orders of scattering. And if we solve those equations, we get some interesting results associated to what happens with the photon while it is in transit through the metasurface. So here I'm showing the population of the probability of finding the photon in the state with a given harmonic and a given geometric phase as a function of time. And we see that there are two time scales associated to the problem. These very fast oscillations, we can actually show that they are Rabi-like oscillations that come only from the geometric phase of the matter atom, so by rotating them. While this envelope here that has a much longer period, it's associated to the contributions coming from the time modulation of the meta atoms. And it's actually easy to understand why the probability also decays as a function of time. It's because the longer the photon interacts with the metasurface, the higher is the chance of exciting order harmonics in the system, and therefore a specific harmonic has to have its probability decaying. Another way to look into this problem is actually to consider some time of interaction and then see what happens as we change the strength of the modulation of spatial temporal modulation. And what we observe in that case is that the stronger the delta alpha, the modulation of the polarizability, the higher are the chances of having our photon populating higher and higher harmonics. In most of the cases, we're going to be working with weak modulation, so we excite only the very few harmonics of the system. So here is just some results regarding what is the density matrix operator for our problem. And I should quickly mention here, I'm showing the modulus of that density matrix operator. And in the axis here, we have the indexes P and P prime that index essentially the frequency harmonics. So fundamental harmonic, first harmonic, second harmonic, and so on and so forth. And the inner columns and lines that you have here, there are two of them associated to right polarization, two to left polarization. And then when this middle index here is 0, means that the photon is propagating normally to the metasurface. When it's 1 or -1, it's being kicked by the geometric phase in the metasurface. So this is the input state, which is just a horizontal, a linear polarization, so equal superposition of left and right polarizations, and impinging normally to the metasurface. If we don't have any spatial temporal modulation, what we see is that there is polarization, a conversion to a state that's a superposition of left and right states that are kicked in opposite directions due to the spin-off coupling. Or in the case where we don't have any geometric phase, but we do put some spatial temporal modulation, we can actually generate entanglement between the frequency and the linear momentum of the photon. And in this second case here, I'm just chose some strength for the interaction to show that we can completely eliminate the fundamental harmonic from our problem. So we can decide which harmonics are present or not in the problem. And in the general case where we have spatial temporal modulation to give a synthetic phase and a geometric phase from rotating the meta atoms, then what we achieve is actually hyperentanglement between frequency, spin, and linear linear momentum of our photons. Okay, so here, the second case that we considered for our space-time metasurfaces was the possibility of generating real photons out of the quantum vacuum through an effect that's called the dynamical Casimir effect, which is essentially the situation where by shaking a boundary, we can show that we are pumping energy into the system and we can convert virtual photons into real ones. This process requires obviously driving, and was originally predicted for mirrors that we would move mechanically. But because the mechanical frequencies that we can achieve are too weak, the production rates of photons were actually too low to be measured. And the dynamical Casimir effect has only been measured, as far as I know, in analog systems where rates as high as 10 to the 6 photons per second can be achieved. And there are various theoretical approaches to deal with this problem. For instance, methods involve parametric oscillators or time-dependent perturbation theory, macroscopic approaches where we enforce time-dependent boundary conditions to the electromagnetic field, or microscopic approaches like this one that was developed by Paulo Américo and Reinaldo, where they consider a multipolar interaction Hamiltonian between the electromagnetic field and the various atoms in a lattice, and they put that lattice to oscillate mechanically, which is somehow a mechanical DC effect. But that can also be achieved, for instance, by considering that rather than modulating the position of the atoms, we can just modulate the resonant frequency of the energy levels of the atomic species. And what we did was to consider what's called a space-time dynamical Casimir effect. That is essentially to modulate, for instance, the lattice positions, but in addition to having the time control, to put a phase depending on the position of each meta-atom and the metasurface. So we have this kind of traveling wave modulation. And we can do the same essentially by modulating the resonant frequencies as a function of space and time. And in both of these cases, we can actually show that the photon pairs generated, they will be entangled in frequency and linear momentum, with the frequency of the generated photon pairs satisfying this relation and their momentum also adding to this imprinted linear kick on the metasurface. We started to do this problem originally for the case of mechanical oscillation. And here is our calculation for the rate of photon generations as a function of the kick that we put into the modulation by modulating this in space. And the interesting feature here to notice is that the rate of generation of right and left circularly polarized photons remains more or less constant as we change the in-plane kick, which at the time we thought, well, this is promising because it means that if we're to do an experiment, I can steer my photons in different directions and keep the rate of photon generation more or less constant. But then there was a big problem, that is when we tried to put some realistic values for atoms trapped and oscillating in an optical lattice with typical modulation frequencies that can be achieved, we get a ridiculously small photon generation rate that it would mean that we have to wait for many orders of magnitude the age of the universe to see a photon pair. So this obviously is a non-go, and we decided then to look again for analog systems based on our idea of space-time modulation of the metasurface, using either electrical or optical modulation of some systems, because we can achieve much higher modulation frequencies. And the system that we actually consider is the one in this figure here, where we have graphene nanodisks that we change the Fermi energy as a function of time and position. And because we are considering isotropic nanodisks, the problems that I'm going to be discussing, there is no geometric phase, but only synthetic phases due to the modulation of the Fermi energy. And why did we consider these nanostructures? Is essentially because in a work that we did with Yuri Muniz from the Institute, we showed that these nanodisks, they support very localized plasmonic resonances that can leak into the far field and generate very and have a very high production of far field photons. And we try to benefit from those resonances, in addition to the fact that we could do the theory very easily to compute the polarizability of these meta-atoms analytically. So what we did was then to consider these graphene metasurfaces, where we bias the Fermi energy, and we looked into the problem via the dipolar Hamiltonian with perturbation theory, and we looked into different kinds of couplings. So we considered the linear phase distribution that I already mentioned before, and here's an example of what happens. For instance, if we look into the pair of photons that are emitted, and we consider the case where they both have the same frequency and equal to the half of frequency of the modulation, and assume that one of the photons is sent up here, we see that by changing the in-plane kick of the modulation, we can steer the direction of the second photon of our entangled pair, and that can be done not only in one plane, but essentially in any direction. And if we do also a different kind of modulation, where we do a spatial-temporal modulation that is rotating around some given center, we can show that we're actually going to generate photons that are vortex-like and have entanglement between energy and angular momentum, with the angular momentum adding to the angular momentum that we are imprinting on the metasurface. So these are my two final slides. Just want to say that it's physically more interesting looking into the one photon rate. So when we integrate, we trace out one of the photons of the problem. And for this nanodisk metasurface that we have investigated, we can show that the rate of generating one photon per unit of momentum per unit of frequency has an expression that looks like this. And there are two things that you should see. One is that all the material properties are embedded in this factor here. And there is this other factor that encodes all the information about the spatial distribution of where the photons are being emitted. And we decided to see how these photons are being emitted as a function of the modulation frequency and the momentum beta. And by looking to the polarizability, you can see that this modulation actually allows us to define some group velocity that involves the modulation, the temporal and the spatial modulations. And this group velocity of the modulation signal can be smaller or larger than the speed of light without any violation of any laws associated to relativity. So in the case where we have the group velocity to be infinity, so no spatial modulation, but only temporal, then we are in the standard case of dynamical Casimir effect, and we can show that the low frequency photon of the pair is going to have an emission spectrum that has a dome-like shape, but it will, and the high frequency photon will be emitted in this cone-like shape with maximum emission happening at this critical angle here. As we start to make the spatial modulation finite so that we break reciprocity at the level of quantum fluctuations, then the system will be in a superluminal modulation regime. And what happens that we see is that the high frequency photon cone starts to be tilted towards the direction of the in-plane kick that we are putting in the metasurface, while the low frequency photon, the dome, starts to get deformed until actually it also starts to be emitted only in the direction where we are putting the momentum modulation. And if we keep increasing the value of beta, we will eventually reach the situation where the group velocity of the signal is equal to the speed of light. And in that case, photons are only emitted at grazing directions and parallel to the kick. And for subluminal modulations, there is no photon creation for the dynamical Casimir effect. So just to finish here, we have then computed what is the spectral emission rate. And as you can see here, we see some very important resonances that appear in the spectrum that are associated to the resonances of the polarizability of the meta-atoms, and that should lead us to enhance the emission and creation of dynamical Casimir photons. And if we put some typical numbers of what we can achieve in these metasurfaces, we can actually show that we can have rates as high as 10 to the 12 photons per second per centimeter square of the metasurface, and we can tune these creation rates as a function of the in-plane kick or the Fermi energy of the graphene nanodisks in our metasurface. So just as a summary, I want to mention that non-reciprocity in electromagnetism is a tricky subject, and it has various subtleties that we need to be aware of. And in our work here, we have done the first demonstration of free space, I would say, extreme non-reciprocity for both linear, for beam steering and focusing. And from what we are planning to do next in this part is actually to consider modulation protocols that are much more complicated than just the sinusoidal waves that we have been thinking so far, so that we can tailor which harmonics to excite from the metasurface. Obviously, the problem becomes much more complicated because now I don't have just that nice diagram that I showed before where the fundamental mode couples to the +-1, that couples to the +-2, but now I actually have full coupling among all the reflection coefficients, and it can be very complicated. But if you want to take a message from this part here, is that you remember that I mentioned invisibility cloaks and metamaterials, and I will let you think this over the day, is that in Harry Potter's movies, the invisibility cloaks there, I'm not sure if they're magical or not, but they are for sure non-reciprocal. And I'll let you think why they are non-reciprocal. And finally, we have also introduced this idea of space-time quantum metasurface, which is a very exciting topic that we've been working regularly nowadays. And these metasurfaces, they can come in various flavors, and they could correspond to classical light interacting with quantum systems like atomic arrays, or situations where we have hybrid quantum classical systems where we embed emitters into dielectric metasurface, or even situations where we have quantum light interacting with quantum metasurfaces made of quantum materials like graphene or other two-dimensional systems. And we have used this to show that we can achieve on-demand manipulation of orbital angular momentum, spin angular momentum, linear momentum, frequency, and other degrees of freedom. And we are currently pursuing experimental demonstrations of some of the aspects that we have proposed theoretically. With that, I want to say thank you again for the invitation. I hope you had a good time with this talk. Remind you that we have this experimental postdoc position associated to this second topic that I was mentioned here. And I'll be happy to answer any questions you may have.
Okay, thank you, Wilton, for the nice presentation, very clear. We have time for questions, comments. Belita, go ahead, please. I think you're muted.
Muted.
Can you hear me now?
Yes.
Você quer pergunta em inglês ou em português?
Tanto faz, pode ser em português.
Eu fiquei curiosa com aquele seu do átomo, meta-átomo, que você mostrou a figura várias vezes, mas tem na página 13, se você quiser ir para a página 13.
13.
São dois anéis concêntricos. Essa montagem me lembra muito os qubits supercondutores, quando você tem superposição da corrente indo para um lado e para o outro. Tem alguma coisa a ver com isso?
Certamente pode ter a ver. O motivo pelo qual nós fizemos, não. Tipicamente, esse tipo de meta-átomo tem sido largamente usado em pessoas, nos grupos fazendo pesquisa em metamateriais, né? A ideia é ter esses split ring resonators. Tipicamente, a gente tem só essa parte interna que quando tem uma metasuperfície estática, né? Como a gente queria colocar uma modulação temporal e aplicar uma voltagem por causa desses diodos aqui, a gente precisou adicionar essas linhas de contato para poder aplicar a voltagem. Além disso, eu devo mencionar que esses caras aqui são, na verdade, bem grandes, né? Eles são, na verdade, tamanho de milímetros para a demonstração que a gente fez. Mas eu...
E aí, esses dispositivos aí que você disse, o que mesmo? O diodo no supercondutor tem junções de Josephson. Essas posições.
Nós tivemos discussões sobre ao longo dessas linhas aqui no grupo, né? E assim, sim, isso entraria na segunda parte do trabalho sobre metasuperfícies quânticas. E nós temos alguns projetos que nós propusemos aqui, e que a gente está esperando para descobrir se eles serão financiados ou não, que vão ao longo dessas linhas.
Então, preste atenção nos qubits de Josephson Junctions.
Sim. É com modulação usando o campo magnético, né? Se eu não estou enganado.
O campo magnético você tem nas duas direções, então você tem momento angular para cima e para baixo simultaneamente. Então, essa é uma superposição não usual, né?
Só para comentar, isso se enquadra perfeitamente no que eu estava mencionando aqui, de que essas metasuperfícies quânticas, que a gente tem essa modulação espaço-temporal, corresponderia nessa situação onde a gente tem luz clássica ou quântica interagindo com sistemas quânticos, né? Onde os meta-átomos, eu mencionei aqui arrays de sistemas atômicos, mas poderiam ser, como você está dizendo, arrays de qubits com conjunção de Josephson.
Muito bom. Tá. Existe algum ponto de contato?
Se alguém quiser discutir mais detalhes, nós temos bastante interesse em fazer pesquisa em várias dessas áreas, tanto do ponto de vista teórico, quanto do ponto de vista experimental. Só para, enfim, acho que nem todo mundo necessariamente sabe como aqui em Los Alamos, mas nós temos essencialmente todas os equipamentos experimentais necessários para fazer essas demonstrações associadas à fabricação, síntese, caracterização, e um grupo experimental muito bom, especialmente na parte de ótica e fotônica, mas certamente há colaboradores na parte also de quântica.
Mas o material que você tem é um metal, né? Esse é um metal.
Para aquela metasuperfície específica que a gente estava pensando num problema clássico, sim, é um metal e a gente usa um diodo no sistema.
Essas experiências são feitas em temperatura ambiente?
Elas foram feitas em temperatura ambiente.
Essa grande diferença, né? Porque os qubits, os supercondutores são baixa temperatura.
Isso é uma das coisas que nós pensamos que pode ser benéfico dessa abordagem que a gente tem com metamateriais, é que a gente não precisa utilizar qualquer tipo de criogenia para baixar a temperatura. É claro que devem surgir outras dificuldades no problema, mas a gente deixa para responder essas dificuldades uma vez que o financiamento é dado.
Bom, outra pergunta rápida. Esse prêmio que você ganhou, Young President?
Não, foi o que eles chamam Early Career Research Award.
É do governo ou é da NSF?
Ele, na verdade, os laboratórios nacionais, eles têm um próprio financiamento interno, né? Então é do Departamento de Energia, mas é uma competição entre todos os jovens cientistas de início de carreira do laboratório. E no ano que eu ganhei, eles financiaram 3 trabalhos na área de pesquisa de materiais. Eles chamam de materiais para o futuro. E o meu foi o único trabalho teórico selecionado, junto com outros 2 experimentais, no laboratório inteiro.
Parabéns.
Obrigado.
Desculpe que eu tomei tanto tempo das perguntas, eu não sei se eu tomei Obrigada.
Obrigado, Pelito. Tem o Felipe.
Tem tempo ainda? Então,
Sim.
Então, Wilton, obrigado aí pela palestra, excelente, e pelo trabalho que você tem feito, parabéns mesmo. Então, a minha pergunta é sobre as estatísticas de intensidades, né? A gente sabe que toda vez que você tem reflexão de ondas eletromagnéticas num plano, com algum tipo de rugosidade, por exemplo, né? Se não há correlação entre as fases da onda refletida, você espera obter a chamada estatística de Rayleigh, né, para as intensidades refletidas. O que ocorre se você, ao mesmo tempo, tiver uma superfície corrugada? Isso é a origem do Spectral, bem conhecido em ótica, né? E, ao mesmo tempo, corrugado e não recíproco. O que você espera obter para pedir, né, para a estatística de intensidade? Já tem alguma predição ou isso já foi feito?
Primeiro, eu não sei responder a sua pergunta nesse momento. Segundo, eu não conheço nenhum trabalho que tenha estudado esse aspecto em materiais não recíprocos. Talvez com sistemas magneto-ópticos exista algum trabalho na literatura, mas como talvez sejam tópicos tão não correlacionados, eu não tenho certeza se tem tantos grupos que tenham olhado e feito esse trabalho necessariamente nisso. Eu diria que não tem nada feito na literatura e eu não sei responder a sua pergunta sobre o que eu necessariamente espero que ocorra nesse caso. Eu precisaria ler mais sobre a estatística que você está falando.
Certo. Bom, isso é boa resposta. Eu tenho uma segunda pergunta mais rápida, que é a seguinte, né? O que acontece quando você tem sistemas... É possível você gerar não reciprocidade em chamados sistemas não hermicianos, né? No sentido que você pode fazer uma engenharia de ganhos e perdas, né? Um meio com ganho e perda, de modo a gerar um sistema não hermiciano, isso é possível?
Não, isso é um erro comum na literatura de várias pessoas, que a ideia de propagação assimétrica e não reciprocidade, né? Como eu mencionei antes, né? Se o sistema for linear, tiver tensores ópticos que são simétricos e for independente do tempo, não interessa se você tem ganho ou perda, o teorema de Lorentz garante que o sistema é recíproco. Então, mesmo que você tenha sistemas não hermitianos com simetria PT, né, paridade e simetria de diversão temporal, o sistema vai ser recíproco. Há alguns trabalhos na literatura, entretanto, que vão dizer que você tem não reciprocidade. E você tem que ler com cuidado esses trabalhos. Porque alguns estão errados. Outros estão corretos e eles de fato conseguem não reciprocidade. Mas a não reciprocidade que eles conseguem não é por causa da simetria PT ou porque você tem ganho. É porque, tipicamente, meios com ganho também envolvem não linearidade. E se é não linear, não tem nenhum motivo para o teorema de Lorentz valer. Além disso, se tiver muitos trabalhos PT também tem modulação temporal, que de novo não tem nenhum motivo para o teorema de Lorentz valer, mas se é estático, esse é um problema independente do tempo, com tensores ópticos lineares, simétricos, e o problema é puramente linear, é recíproco.
Certo. Então, a origem está no fato de que esses sistemas com ganho geralmente são não lineares, essa é a origem, né? Tá. Certo. Ok. Tá bom, Wilton. Muito obrigado e parabéns aí mais uma vez. Vou passar a palavra aí para o Murilo.
Obrigado, Felipe. Tem Farina, por favor.
Oi, Wilton. Bom, muito obrigado aí pela excelente palestra. Muito bom vê-lo novamente aí. Já que você falou em efeito Casimir dinâmico e botou até aquela figurinha daquele experimento de modelos análogos, né, que tem uma linha de transmissão semi-infinita, terminada por um squid, através do qual você tem um fluxo magnético variável com o tempo, e isso acaba simulando o movimento, né? Foi assim que mediram o efeito Casimir dinâmico pela primeira vez. Aí eu queria ouvir a sua opinião sobre algo que uma vez a gente conversou muito rapidamente, mas agora que você mexeu mais com isso, você acha que faria sentido pegar uma folha de grafeno, aplicar um campo magnético oscilante perpendicular a essa folha? Isso também acabaria simulando condições de contorno dependentes do tempo, que de uma certa forma simulariam o movimento, mesmo o grafeno estando parado. Você acha que teria chance de ter um número de fótons de Casimir dinâmico que pudessem ser mensuráveis?
A minha resposta é sim e não, ao mesmo tempo. Sim, vai ter um efeito Casimir dinâmico que vai produzir um número bastante alto de quantas de luz, entretanto, porque você modulou o campo magnético. Eu acho que a abordagem é muito parecida com a que a gente, na verdade, fez. Só que como você está considerando uma folha de grafeno infinita, o que eu espero que vai acontecer é que você vai excitar magnetoplasmons no sistema. Só vão ser ondas de superfície que vão ficar confinadas na superfície do grafeno. Então, para fazer um experimento e medir geração de pares de plasmons emaranhados, acho que esse valor, a taxa de geração vai ser bastante alta. O problema é que os experimentos tipicamente medem fótons, né? Porque é mais fácil de você detectar e medir correlações. Na verdade, eu não sei nenhum experimento com plasmons que mede diretamente emaranhamento de plasmons ou pelo menos correlação temporal, né? Tipicamente você tem que converter eles para fótons. E nesse caso, então, essa primeira resposta é sim, a taxa vai ser grande e não acho que você vai ter muitos fótons sendo gerados no sistema. Se você, entretanto, considerar que em vez de ter uma folha de grafeno infinita, mas você considerar, por exemplo, esses nanodiscos que eu estava mencionando anteriormente, mas na presença de um campo magnético, eu espero gerar modos magnetoplasmônicos que vão ser espalhados pela borda do nanodisco, e esse espalhamento vai gerar, então, fótons com alta taxa de fótons por segundo.
Maravilha, obrigado. Só mais uma coisa, vocês entraram em contato com algum grupo experimental de Casimir dinâmico?
Não, nós não entramos em contato com nenhum grupo de Casimir dinâmico. Nós temos um projeto que está se encerrando sobre a parte teórica e nós estamos tentando trabalhar uma possível continuação experimental do nosso projeto em colaboração interna aqui no próprio laboratório. A gente tem um grupo de ótica e laboratórios de ótica e de fabricação muito forte e que todos esses metamateriais feitos de grafeno a gente consegue fabricar. Eu mostrei aqui, a gente consegue fazer a modulação utilizando esses gratings ópticos com interferência de dois lasers. E a parte complicada para a gente aqui, eu diria que é mais a parte relacionada à ótica quântica, né, de detecção dos fótons. E é por esse motivo, inclusive, pelo qual a gente está procurando por um pós-doc experimental, de preferência com experiência em experimentos em ótica quântica, mas qualquer bom candidato certamente funciona.
Maravilha. Mais uma vez, cara, parabéns pela palestra e obrigado, hein?
Obrigado, Fariana. Bom, eu não vejo mais nenhuma mão levantada, então agradecer novamente o Wilton, em nome do Instituto, pela palestra, por ter aceitado o convite, né, e pela ótima palestra, e nos vemos no próximo colóquio em data a ser definida. Tá? Então, aplausos ao Wilton.
O Wilton está presenciando aí nossos aplausos analógicos.
Obrigado, gente. Cortou um pouco, mas eu entendi que você agradeceu e aplaudiu. Por algum motivo, minha internet travou. Obrigado novamente pelo convite. Obrigado pelas perguntas. Foi um prazer novamente entrar em contato com as pessoas com quem eu convivi durante 8 anos da minha vida no Instituto de Física. E é sempre um prazer falar com vocês toda vez que eu tenho a oportunidade de ir ao Brasil, e eu eventualmente sempre dou uma passada no Instituto de Física para conversar com a galera. E se alguém tiver algum interesse e quiser discutir algum aspecto teórico ou experimental desses projetos, fique à vontade em me escrever. Como eu mencionei, nós temos sempre possibilidade para postdocs e até mesmo estudantes para visitar o laboratório, como oficialmente é chamado um estágio aqui no laboratório, porque nós não somos uma instituição de ensino, mas acho que se configuraria como um sanduíche.
Deixa eu perguntar uma coisa. Você não teve problema de ter esse trabalho por ser brasileiro? Laboratórios nacionais, eles em geral não contratam estrangeiro.
A divisão teórica ela é majoritariamente formada, assim, boa parte da divisão teórica é formada por estrangeiros. No laboratório, um grande processo de investigação de antecedentes, e uma vez que toda a papelada é aprovada, e se você segue as regras, não há problemas em certas áreas de pesquisa para serem feitas. Eu não tive nenhum problema especificamente sobre esses trabalhos para as minhas condições.
Sorte sua.
Algumas pessoas até ganham a nacionalidade, viram cidadãos, né? Mas muita gente ainda é estrangeiro, né? E lá na Theoretical Division.
A divisão teórica é uma das maiores divisões do laboratório. Acho que tem atualmente mais de 300 pesquisadores, deve ser uns 250 pesquisadores regulares, eu chutaria uns 80, 90 pós-docs, e eu posso dizer que a maioria dos pós-docs são estrangeiros. Então, assim, tem todo esse processo burocrático interno que só quando você vem para cá você descobre que existe, mas assim, uma vez que isso é feito, não há grandes limitações. E, na dúvida, a gente sempre pergunta para alguém que sabe a resposta sobre como proceder para evitar problemas. Eu, felizmente, não tive nenhum problema quanto a isso.
Tá bom. Tchau, gente.
Ok, gente.
Obrigada. Parabéns.
Tchau, obrigado.
Tchau.
Obrigado, Wilton. Um abraço. Obrigado.
Até mais.
Valeu, Wilton.